Hello. We are going to talk about 6.2 today, the definite integral and net change. This lecture shouldn't be as long as the last one, which I'm sure you're happy about. I really just want to highlight a couple of things. I think the book does a pretty good job of going through this. So I just really want to do some examples for you and kind of highlight a couple important things about the definite integral that you should know. So you should have copied down this definition already, but let's just really quick copy this down just so we have it. To come back to. So it has all this set up, let f of x be continuous. Remember, continuity just means that there are no holes or breaks in the graph. You can draw it without lifting your pencil. And we want it to be continuous on some interval AB, and it has antiderivative capital F. Okay, so the definite integral then, and remember how we write this now, it's the integral sign from A to B of this function lowercase f dx. Okay, that's the variable of integration. These are our limits of integration. Is going to equal, so this is just a definition. We'll talk about more about this being a theorem in 6.3, but this is what we're defining the definite integral to be. We are defining it to be the antiderivative, or an antiderivative, right? That's the capital F of little f. I want to evaluate that function at b, and then I'm going to subtract the antiderivative evaluated at a, which you already saw in the book. Another way of writing this, because mathematicians are lazy, I always try and find shorthand for writing things. And this is usually what will happen. Usually what we'll do when we take this, I'm going to do some examples for you. Antiderivative is, I'll write this first and then we'll get to this point. But for right now, this is just notation. Okay, the a and the b are what we call limits of integration. Okay, a is the lower bound. B is usually called the upper bound. Okay, so a and b are your limits of integration. And then, so what does this all mean, right? That's what you're asking. So great, Sarah, I take, the antiderivative and I take b and I subtract a from it. But what does that actually mean? So the big idea in this section is that when you take this f of b minus f of a, what this means, this is just the net change, okay, the net change of the antiderivative, so f of x, as x changes from a to b. Whoa, that was a little weird. From a to b, which makes sense, right? Because we know subtraction, that's a difference of two things, and a difference gives us a change. If my bank account changes from 1,000 to 600, what was my net change? It was a negative 400, right? I would take 600 minus 1,000, where I end up minus where I started. So this is the net change in f of x. You might be asking yourself, well, hey guys, what happened to the c, right? Now, we could have put in c here. If I had done f of x plus c, right, some constant, because remember we can use any antiderivative, look at what would happen if I plug b into this. That c is a constant, so the c just stays. And now I'm going to subtract the a plugged in. Again, the c is just a constant, so the c just stays. And if you take that negative through, you see we get just f of b minus f of a, and these c's go ahead and cancel out. So that's why we don't put that c there, is because no matter what we chose that c to be, it would go ahead and cancel out. And then I'm just looking up in my book right now. I would like you to look maybe at the graphs on page 301 and 302, and it gives you a nice visual representation of what that looks like graphically. Okay, how do we actually think about the change in my function graphically? So again, that's page, and I know you've already read the book, this section, and so you probably have this in your notes already, but you 301 and 302. All right, so before we get going too crazy here, there are also some properties. These are the boxes in the book that I asked you to write in your notes. So some of the properties of, of integration. If I have definite integrals, I can break up, Okay, integration across addition or subtraction. Now, we usually won't actually break this up. We'll probably just leave it all as 1. But if I wanted to, I could think of taking the antiderivative, or the definite integral of f plus or minus the definite integral of g. Okay, so I can break up that integration. That's only true for addition and subtraction. People, it's not true for multiplication and division, so don't be doing it. All right? All right, good. The other thing I can do if I want to is if I have a constant times my function, whoops, I can actually pull that constant out and just take the constant times the antiderivative. Or, oh, excuse me, the definite integral. It's late in the day and I'm just blinking a little bit. And this kind of makes sense. You can see a pretty easy proof of this. You know, if you look at this side, this purple, we'll call this the purple side. If I kind of look at that, I would have k times f of b minus k times f of a, right? Because that k doesn't affect my antiderivative. But look at what I'd have over here. I would have, if I did the k after you took the definite integral, then I would just have k times f of a minus f of b. And you can see that those two are definitely the same. Okay. Let's look at another property of definite integrals that's kind of interesting to think about. This will be property 3. And then we'll do a bunch of examples and one applied example, and then we'll call again. So this one's kind of an interesting one. If I'm integrating from a to b of f of x dx, if I switch the limits of integration, so I'm going to do b first and then a, what that does is put a negative. And that kind of makes sense too, right? Because if we think about this side right here, this is f of b, capital F, minus capital F of a. But over here, what would this be? Put some parentheses here. Well, now I'm going to be taking capital F of a first, right? Because that's my top limit of integration, or my upper limit of integration, minus f of b. So it makes sense that if I take this negative through, you can see that those two are true. When you switch the order of subtraction, you get the opposite sign. So for number 4, if I have this is the 4th property. If I take the integral from a to a of dx, well, that's just 0. Think about net change, right? If this is asking, what is the net change of my account? If I have $1,000 in my checking account and it stays at $1,000, what is my net change? Well, it's 0. Maybe that's good or bad. I didn't spend any money, but I didn't get any money either. So that kind of makes sense, and that's an easy one to prove because this would just be f of a minus f of a, right? That's what my limits of integration are. And then the last one here that is kind of interesting, I think, that, you might practice this a little bit on your homework. We won't really use this rule for a little while. We'll use it, well, we might use it in the next section, but we won't really use it for too long. If I go from A to C, so I want the net change from A to C, and then I want the net change from C to B, okay, that really is just the total net change from A to B. And C doesn't have to be between A and B. This is kind of an interesting one because C really can be any number. As long as these two are matching, then I can just write that as one integral from A to B. The way we can prove this, pretty easy. What's the definition of this definite integral? It's capital F of C minus capital F of A. Okay, now this guy here, we have plus, what would this be? Capital F of B minus capital F of C. If you notice, these F of C's cancel, and if I just switch the order here, that just equals, well, not switch the order, just rewrite it, right, with my negative second. That equals F of B minus F of A, which by definition is that guy right there. So those are the 5 properties of definite integrals that are good to know. I think there's some of your homework problems that are kind of like that. But what I would like to do really just now is do some examples of these guys. So I'm going to add a new, one second. Whoops, that is not what I want. Add a new layer here. So let's look at some examples of doing this stuff. Start off kind of easy. So let's just evaluate from, I don't know, 2 to 6, how about x plus 1? The function x plus 1 dx. Again, what is this asking you to find? It's asking you to find the net change in the antiderivative of x plus 1 as x changes from 2 to 6. So your first step when you're doing these is to take that antiderivative. So the antiderivative of x, if you remember, is 1/2 x squared. Antiderivative of 1 is just x. We don't need the c in this case because the c's cancel. And then we're evaluating this from 2 to 6. I want to see your work on your, I need to see your work on your homework, right? Don't just put the answer when you do these. I want to see your steps. And make sure when you write this step that you put that evaluated from 2 to 6, okay? This guy doesn't equal a function, it equals a number. And so finally what we do is to take this guy right here, this function, this is my capital F of x, right? And I want to evaluate it at 6, and then I want to evaluate it at 2. So if I put in 6, I think 6 squared is 36, I can do that, plus 6, there's my F of 6, minus, make sure you put parentheses unless you go ahead and just simplify that in your head, because we are subtracting that entire sum there. And so it looks like I get 18 plus 6, which is 24. That would be F of 6, or my capital F of 6, minus 2 plus 2, which is 4. So what do I have? What is my answer? It is 20. And again, what does that mean? That means that this function right here, 1/2 x squared plus x, has a net change of 20. Granted, I don't know what my units are, right? It's just a net change of 20 as x changes from 2 to 6. So if I were to look at that distance between those two function values, that distance would be 20. All right, let's try another one. What about 0 to 1 of e to the 3x? How about plus the square root of x? That might be kind of fun. Who knows? I think it's all fun. So, all right, so we're going to take the antiderivative again. I'm going to kind of rewrite this square root of x kind of down here just for a little fun as x to the 1/2 because I know I'm going to be adding 1, right, and dividing by it. So antiderivative of e to the 3x, remember, is 1/3 e to the 3x. Okay, and then I'm going to add 1 to 1/2. So if I add 1 to 1/2, that gives me 3/2. So I'm just doing a little bit of side work. And then I divide by 3/2. So dividing by 3/2, remember, we flip it and multiply. So that would actually be plus 2/3 x to the 3/2, all evaluated from 0 to 1. Okay, so I'm going to plug in 1. If I plug in 1, I get 1/3 e to the 3rd power. I'm going to just leave it like that. If you want to make it a approximation of that, that's fine. You can write out the number. You're going to have some decimals there. Won't be exact, which is okay, but I would just leave it. I would totally accept it as e cubed. Okay, if I put in 1 here, well, 1 to any power, right, is just 1. So that's plus 2/3. And then minus, again, parentheses. If I put in 0, e to the 0 is 1. So I get minus 1/3. 0 to anything is 0. Okay, and so if we simplify this a little bit, it looks like I get 1/3 e to the 3rd. 2/3 minus 1/3 is 1/3. And that's my final answer. And if you're like me and you can't stand this, I would factor that 1/3 out. But you don't have to. That's just me and my OCD issues when it comes to writing mathematics. It'll be fine. I'm fine. I should get some help for it, but I'm fine. So that's our answer right there, that 1/3 e cubed plus 1. Okay, that again is the net change of my antiderivative. That means this function right here as x changes from 0 to 1. All right, I'm going to do one more example for you, and then I think we'll call it good for this one. So let me just clear this out. I want to do an example, applied example. So this will take a moment for me to write this out. But let's say that we have a company that manufactures TVs. So a company manufactures X TVs per month. Okay. And so here's what we know about this. The marginal profit Remember what marginal cost, marginal profit, marginal revenue, all that means is it's the derivative of the cost, it's, the corresponding function. Derivative of the cost function, derivative of the profit function. Sorry, I'm trying to fix my, there we go. The marginal profit, excuse me. The marginal profit in dollars, so not thousands of dollars, but just in dollars, is given by, and this is profit per month, right? Because we're talking about TVs per month. And so here's what we know. P primed of X, because that's the marginal profit, that's the rate of change of my profit, based on X number of TVs produced, right? That's what that X is saying, 0.1. So 165 minus 0.1X. And then here, I'm just going to give you a little bit of information about the domain. This guy actually isn't going to give us too much. Well, it's not going to really come into actually doing the problem. But sometimes these mathematical models, right, the way they model our information, maybe it's only really accurate, for up to 4,000 TVs. Then after that, maybe my model just kind of goes haywire and doesn't really, describe the situation well. So that's just sometimes you'll see that with your X's because this model is only really good for that interval. Okay, so if the company currently produces 1,500 TVs per month, determine, it's a lot of writing, the net change in profit if production is increased to 1,600. 1,600 TVs per month. Okay, so if we're currently at 1,500 TVs per month, what we want to know, and 1,500 and 1,600 lie in this interval, so this is a valid mathematical model for that. So what do I want to find? I want to find the net change in profit, right? Net change in profit. Well, here's the great thing. I know that if I take the antiderivative of P primed, I just get P. So the antiderivative of my marginal profit gives me my profit function by definition. So really what this is it's just a definite integral problem. I'm going to start with 1,500 TVs, okay? And I want to increase production to 1,600. So I want to know the net change in profit going from 1,500 TVs to 1,600 of my profit function. So if I put its derivative here, then when I take the antiderivative, I will get my profit function. Sweet. All right, let's see what happens. So antiderivative of 165, 165x, correct? Minus, now I'm going to have x squared, but I need to divide by 2, so 0.1 divided by 2, I didn't give myself enough room, is 0.05. Right, too big, x squared, and I'm evaluating this again. You should be evaluating this from 1,500 to 1,600. Just want to get on my soapbox for one moment and say you should really be trying to mimic the way that I do these problems. Not that I'm cocky or anything, but I'm pretty good at mathematics, and the way I write these problems is how you should be trying to write your problems also in your work. So the equal signs coming over, you should be writing this evaluated at and showing me your work, okay? And then that helps too when I grade your exams. If you can show me your work, if you make a silly mistake, like forget to divide by 2 or something, I can give you most of the credit for the problem because you're understanding to take the derivative and evaluate it. Okay, so make sure that you're actually showing me your work. So 165 times 1,600, and my calculator will be aiding me in this calculation, squared minus 165 times 1,500. Again, the change in profit as we go from 1,500 to 1,600. I apologize. I should have done this before I started recording this lecture. I think it's 1,000. We did this with my face-to-face class, and I believe we got 1,000. But let me make sure. And I'm just putting this in all at once, making, sure that I put parentheses around. Oh, I did something wrong there. I got a negative, like 110,000. I don't think that's correct. Making sure to put parentheses around, around, all of this stuff. Now, what I get is I get $1,000. So a lot of times on these word problems, I'm going to ask you to write a sentence to describe your answer. So what does that 1,000 mean? That means that the profit, now it's positive, so that means we're going to increase. Profit, whoops, let's do the net change. The net change, I'm not going to be able to fit this, in profit is an increase of $1,000 when production increases to 1,600. Okay. Could that have been like a negative number? Absolutely. If we get a negative number, that says that my profit decreases. How would profit decrease if we're making more TVs? Well, remember, when we're making more TVs, that means we have higher costs associated, and profit is your revenue minus your cost. So even though we got a positive, there might be, if I tried to go from 1,500 maybe to 2,000, you might see a change in profit that's negative. As always, let me know if you have any questions as you go through this section.